we introduce 3D human pose estimation from tactile signals. Daily human activities are guided by the tactile interactions between human and the ground. Leveraging such interactions and using vision as supervision, we present a 3D human pose estimation approach using only the pressure maps recorded by a tactile sensing carpet. We first develop a high-density, large-scale tactile sensing carpet spanning 36 square feet with over 9,000 pressure sensors. Our system enables real-time recordings of high-resolution human-ground tactile interactions. We collect over 2 million synchronized tactile and visual frames on 10 different individuals performing a diverse set of daily activities. Due to the spatial correlation between the human skeleton and tactile signal over the floor plane, we are able to perform data augmentation and synthesis by rotating, shifting, and combining the recorded dataset. We capture visual data with 2 synchronized and calibrated cameras. In order to annotate the ground truth human pose in a scalable manner, we leverage a state-of-the-art vision-based system, OpenPose, to generate 2D skeleton from the RGB images. We then triangulate the 2D skeleton and apply a 3D Gaussian filter to generate a 3D keypoint confidence map. Employing the synchronized visual information as supervision, our model takes in a sequence of tactile frames and outputs the 3D keypoint confidence map for each of the 21 keypoints. Details can be found in our paper. Our model predicts the 3D human pose from a diverse set of daily activities, including walking, sitting, lying, and exercising. The ground truth here is captured by the cameras and extracted by OpenPose, while the prediction is generated from our model using only the tactile frames as input. Our predicted human pose smoothly transitions along the corresponding trajectory, with the average localization error less than 10 cm. The predictions do not rely on any visual information and therefore are not affected by visual obstructions or limited field of view, which are common challenges in vision-based human pose estimation. The prediction on upper body, especially the arms, are generally less accurate than the ones on the lower body and the feet. This agrees with our observation that the movement of arms or the upper body seldom affects the force distribution on the foot pressure maps. Also, the model fails to predict the pose where actions are performed without notable physical contact with the floor. For example, the free-floating feet during rolling. By applying a linear classifier on the tactile feature map, our model also shows the capability to facilitate downstream classification tasks. Here, classification is performed on 10 actions, including squatting, bending, twisting, sit-up, push-up, rolling, waist turning, stepping, lunging, and standing on toes. We further extend our model for multi-person pose estimation. Using only the tactile information, our model localizes each individual and predicts his or her 3D pose with the localization error less than 15 cm. In conclusion, we believe our work opens up new opportunities for human pose estimation using a sensing modality that is different and complementary to the vision system. It is unaffected by visual obstruction in a seamless and confidential manner, with potential applications in smart homes, healthcare, and gaming.